Hello, everybody. My name is Matthew Morris. You can see up there. I first want to start off with an apology from my co-presenter. Unfortunately, Scott Hotaling can't join us today. He fell ill this morning. So everybody take care of yourselves. He's feeling okay, but didn't want to risk exposing anybody or coming into a room not feeling super great. With that said, I want to thank Aaron for helping me get set up today. And I just want to also say thanks for coming. I'm really excited to share with y'all some of the work we've been doing on features known as rock glaciers. First, I want to do an informal poll. Raise your hand if you've heard of rock glaciers before. OK, so we've got a few folks in the audience. I hope to change that number to 100% by the end of today. Generally, we're going to be talking about rock glaciers through the lens of a water resource. A lot of talks today have talked about the Great Salt Lake, talked about the Bear River, talked about downstream water supply. I'm going to bring us back up into the mountains to talk about the water towers that stand in the Wasatch behind us, thinking about not just the snowpack, but other types of water resources that we haven't considered thus yet that are not being put into our water resource models or water supply models, and some research that we're actively pursuing to try to answer some of these questions about how much water might come out of these features. This is a Scott slide here. Scott is the head of this group, SURMOUNT, the Consortium for Integrated Research in Western Mountains. It's currently an email listserv that includes over 1,000 agency scientists, managers of different levels and different state, county, federal levels, as well as academics. If this is a listserv that could be interesting to you, if you need another set of either job postings or potential grant emails that you might see, take a picture of this QR code and join the listserv. It's handed down from Connie Miller, who's now retired from the U.S. Forest Service. And Scott is now the manager of that listserv. So please feel free to take a picture and sign up. I know that we all are remiss to have more emails, but this is a pretty useful listserv. And it doesn't send a lot of emails, at least not every day. With that, I want to get started on more of the story of today's talk. So we're all familiar with climate change. This is just a good example of another proxy we can look at of sea ice in the in the Arctic Ocean, and think about how our planet is warming. Either think about it conceptually or think about it from an anxiety-inducing alarmist standpoint, which is my usual go-to. But we also have to think about climate change not just at these really high latitudes, but how is it affecting us in the Intermountain West? And a great way to highlight that is a photo like this. So this is Glacier National Park in 1932. Some folks for scale there in the foreground, and they're standing on glacial ice. But if we zoom forward about 50 years, exact same place, there's no ice anymore. So let's go back and forth here. Pretty well matched photo, but a lot of melting of superficial glacial ice in 50 years. And this is not just an event that takes place in the higher latitudes of the Rockies, but also here in Utah. Utah is not immune to climate change. So just highlighting that in the last century or so, we've had over almost 2 degrees Fahrenheit of warming across the state of Utah. We've felt that in many different ways that I'll talk about briefly. Most notably our really hot summers and also our warming winter nights as well. But also in our snowpack. So across the West, this is data from the NRCS SNOTEL system, but just highlighting the trend really that there's declining snowpack through time. This is probably not news to most of you. And in particular, this is looking at April snowpack, so peak snowpack before the melt season starts. And from 1955 to 2012, we've had declining snowpack. And for Utah, we've had roughly a 20% decline in the peak snowpack in April since 1980. And this includes our most recent bumper crop of last winter, which we all remember as an amazing snow year. So we still have a declining trend. In addition to decreases in snow, we also have shifting precipitation regimes. So this is a modeling study, Giles et al. 2012, which shows here in this plot, or actually this next one, how the warmer colors are showing decreases in snowfall while we're having increases in rainfall in the next half century. So we're not only warming, but we're shifting from more snow-dominated to potentially rain-dominated systems. And this is, again, not news to many people in the room. And also, as we look forward, we think about snow as our main water resource. We think about it as the thing that recharges the Great Salt Lake, We just heard this morning how 60% of Salt Lake City's water comes from 5 or 6 watersheds that are a large part contributed through snowmelt and through snow through the winter. And that's really concerning if we have less snow in the future. And just to heighten your anxiety a bit more, here's a 2021 paper that looked at the Colorado River Basin looking towards the future in the next to 2100, highlighting there could be years like 2062 or 2079 when a majority of the upper Colorado River Basin is snow-free through the winter. Again, being that it's such a snowfall-dominated system in the mountains, this is really concerning for like the longevity of our water supply, but also that integral base flow we count on in the late summer. So I want to present this doom and gloom picture, but then also give you a thread of hope potentially. The idea that there could be an underutilized or poorly understood water supply out there already that people haven't really been thinking about. And so I want to change that, give you that perspective today. And what I'm going to talk about, because you know from the title of my talk, are these features known as rock glaciers. So this is a drone video from the Austrian Alps. And you can see bedrock here in the background. But then there's this big talus pile here that's sort of lumpy, and it has a steep front on it. As the drone comes around, you can see it's actually really quite steep. And this is a rock glacier. So you can all say now that you've seen a rock glacier. Maybe not in person, but we'll up that percentage of that poll at the beginning. And what is a rock glacier? It looks like a pile of talus. But there's a bit more subtlety to what's going on in these systems. And we have a bunch of rock glaciers here in Utah, actually. So this is the Timp Rock Glacier. Right? Who's hiked up to Timp or been up to Emerald Lake? Okay, quite a few folks. Emerald Lake is right here. So if you've ever been to the lake, you saw a rock glacier in the background. So this is a loamy, bumpy surface. This is a rock glacier here in Snowbird, just west of, or east of Gad Valley. Notice there's like a lobate shape here on the front. And these look very different than what I put here on the left. These are your more classical ice glaciers, which we don't really have very many of, or really any here in Utah. But if you think of the North Cascades, here's Mount Baker, showing glacial retreat since the 80s. Or here is an Alps. This is a glacier in the Alps, one of the longest glaciers in Europe. These are the glaciers we think of when somebody says glacial ice or climate change is shrinking glaciers. And maybe now we can start to talk more about what are these features that we have quite a few of here in Utah. We don't really have many glaciers that look like this, but we have a lot of features that look like this. And I want to just provide a little background for what if you were to cut through a rock glacier, what would you likely see? And just generally, the definition of a rock glacier is pretty basic. It's masses of talus or debris formed by active deformation of internal ice. And if you think of it as a piece of a pie that you cut down and look at the layers, you could think of a couple of meters to tens of meters of ice that then has talus or rocks on top of it. So that's what this darker colored stuff is here. And you don't need a lot of rocks. Less than a meter of rock, you can insulate ice year-round, even if it gets up to the 80s or even low 90s. The ice down here doesn't know that it's a hot day in July in Salt Lake. And then you have some amount of melt of that ice, and then the ice, by the time you get to that steep front, is sort of broken into pieces. But the ice is holding the rocks together. And if you're familiar with the term angle of repose, these often have very steep fronts, about 40, 45 degrees, because the ice is holding the rocks in place. And the cool thing about rock glaciers is they can grow to really long lengths. This is one in Alaska. It's on Sourdough Peak. Because their melt rates are really slow, they just keep growing and sort of look like big worms on the mountains as they go down. All right, so this is all well and good, a conceptual model of rock glaciers. But the remaining question is, what do the rock glaciers in Utah look like? I've shown you some pictures, but is there actually ice in a rock glacier in Utah? Well, I can show you now that that is definitely true. This is a picture in Little Cottonwood. This is one of my former colleagues, John Solder at the USGS. And we hiked up and found a couple of meters of massive glacial ice exposed under talus. We were very lucky to see this exposure. But we can now say that there is ice in rock glaciers in Utah. Additionally, there's another exposure, intermittent, on Timp, where you can see here, this goes down probably about 7 or 8 meters underneath this sort of carapace of talus. And that's all glacial ice. Uncertain on the age at this point. But there is ice in rock glaciers in Utah. Additionally, we know that they're moving. They're creeping downhill, another indicator that there's internal ice. Okay, so we know what a rock glacier is. We know that they have ice here in Utah. How many are actually around the state of Utah? This is a map showing a rock glacier inventory in the western US. There's about 10,000 of them. If we zoom into Utah, we have over 800 rock glaciers that have been mapped throughout the state. This is an inventory from Andrew Fountain's group at Portland State. And most rock glaciers are located in the Uintas, and then secondarily in the Wasatch, as well as the Plateau Country, and then the Abajos, Henrys, and LaSalles in southern Utah. But if we zoom in more locally, I've shown you some examples in Snowbird. There's a bunch of rock glaciers in Brighton as well, just using the ski areas as places lots of folks have been. They have this lobe shape to them. And if we look at the watersheds that have been talked about today, how many rock glaciers are in each of those? So north, notice the north arrow. I'm a big map fan. North is to the left now, and we're looking along the Wasatch. So this is the Weber River. It has 34 rock glaciers in it. Most of them are in the Uintas, a few in the Wasatch. Big Cottonwood has about 11. Little Cottonwood, almost 30. And then 10 for Dry Creek, Bells, and American Fork. And then the Provo River catchment has about 11. And you may look at this map and say, okay, there's rock glaciers. They don't seem like a big deal. They're very small on the footprint of the landscape. But as a geomorphologist, that's my technical term from my field, I think about not only how do they map, but how do they sit in the landscape. So I'm going to show you next why these could be important. So this plot here on the top left, this is all of the elevations in Little Cottonwood Canyon. If you just took a map of Little Cottonwood and then made a histogram or a chart like this of how much area is at each elevation. And you can see a lot of that area is concentrated around 3,000 meters above sea level. And then this is a plot of where do all the rock glaciers fall. So most of them are about 3,000 to 3,250. And if you do a little bit of division, here you can see what percentage coverage do rock glaciers make of each of those little bands in that histogram. And you can see around 3,000 meters above sea level, rock glaciers cover almost 70% of the land surface in Little Cottonwood. So they may look in map view like they're not that significant, but if you spread out where are the elevations in the landscape, rock glaciers actually cover quite a bit of the Earth's surface. So how do we talk about rock glaciers and climate change? I got you very depressed at the beginning of the talk. And we talk a lot about how quickly these ice glaciers are melting. Well, let's look at rock glaciers. And there's been some work on rock glaciers melting with climate change. So this is just showing the surface of a rock glacier in Europe, along with a ground-penetrating radar image of ice in a rock glacier. And this study was able to show that over 70 years, there was almost zero net balance or net change in a rock glacier's mass. Meanwhile, ice glaciers nearby were shrinking really rapidly on the order of 5 meters of loss per year. So it looks like rock glaciers are really good at insulating. They don't melt very quickly, which is something I shared earlier. But we want to think about how generalizable is this difference. And this is something we don't quite know a lot about in Utah, but we're trying to really nail down. We want to understand what proportion of our stream flow is coming from rock glaciers. I showed you where they are. I showed you how they sit in elevation. But we really want to know how much water is coming out of them. If they don't appear to be melting very quickly, might they melt more quickly in the future? How much are they melting right now? So this is the outflow of a rock glacier in Little Cottonwood Creek, or Little Cottonwood Canyon. This is an active channel flowing at least maybe 5-10 CFS throughout the late summer into even October. And it's about 0 to 1 degrees Celsius year-round, which means it's melting ice or touching ice. And I've been able to instrument this stream. We collected stable isotopes throughout the summer. TBD on the data for that. But we have a few studies we can draw upon about how much water is contributed from these. So in one study, this is a 2023 paper. This is an experimental basin in the Alps. The rock glaciers only make up 40% of the catchment, but they were contributing 60% of summer base flow. So not a lot of water coming out of the non-rock glacier part of the catchment, but majority of the water is coming out of the rock glaciers. And then we have a Utah-specific paper recently. In the Uintas, Jeff Moore was able to show that rock glacier melt maybe 25% of base flow coming out of these high alpine catchments in the Uintas, another one of our big water towers in the upper Colorado. And I just wanted to shift that perspective of not just rock glaciers as a cool feature, but maybe rock glaciers as a water resource. And this builds on a paper from 2018 looking at rock glaciers as potentially globally significant water stores. So this paper shows that in North America, there might be on the order of 15.5 gigatons of water stored in rock glaciers. And we're just going to go down a rabbit hole here of some division really quickly. So 1 gigaton is a cubic kilometer. That's about 1 billion cubic meters. 1 acre foot is 1,200 cubic meters roughly. And if we do a little bit of division here, there's maybe, what is that, 12.5 million acre feet of water in rock glaciers in North America, not specifically Utah, but across the whole continent. And that's about 3.3 Flaming Gorge reservoirs worth of water. So that's nothing to sneeze at, I would say, particularly if it's not been accounted for in any other model of our water resources. And not only is a rock glacier significant potentially from a water resource standpoint, but they also touch on biology. So there's a endangered stonefly, Lednia tutana, which is found in Glacier National Park and in the Grand Tetons, only in streams fed by rock glaciers. So we want to think about the biologic system. Here's some of these really cute stonefly videos that Scott's captured. We want to think about the whole biological system, not just our water resource question, but could streams that are really cold be biological refugia moving forward for other species? We think about them as potentially a place where either stoneflies or moving up the trophic levels, talking about our cute plushy pika friends, or even bull trout might be able to persist for longer periods in a warmer climate because we know the streams will have water that is cold. And we think of our landscape today, this is a picture perhaps of the Tetons where we have a little mix of ice glaciers and rock glaciers. But in our climate future, the ice glaciers will retreat and melt and maybe transition to rock glaciers. But in our climate future, rock glaciers will also be around. So we want to understand these phenomenon. So in conclusion, Utah is warming and our snowpack is in decline. But climate projections, unfortunately, also indicate that by 2060, we could see, in at least the upper Colorado, winters without much snowpack. But rock glaciers are widespread around Utah, and perhaps they might represent a climate-resilient water source due to their insulating debris cover. And they may also be already buffering our mountain streams. We're not sure. And just this big highlight here, there's quite a lot of water in rock glaciers through North America. We still have a lot of unknowns, though. I don't want to sell you down just on a whole lot of promise. We don't know, for instance, how much water is in Utah's rock glaciers, but we're currently working on this estimate. We also don't know how much rock glaciers contribute to summer stream flows. We're getting at that from our last summer observations, and next summer. So we're going to go out and deploy more pressure transducers. And we also ask the question, are we not even accounting for these already? Maybe they're contributing quite a bit to our streams, and we don't even realize it. And then what does this mean for future stream flow? Will we see declines in rock glacier ice melt? Eventually, all the ice glaciers might melt. But will rock glaciers be around for 100 years, or will they melt very quickly in the next 25? And then how many of our rock glaciers are actually contributing to stream flow? And finally, how important are these glaciers to the cold water biodiversity that we see here in Utah? And with that, I'll take any questions in our few remaining minutes. And if you have any questions, Aaron here is going to run the mic around so we can record the questions.
So I know ice glaciers are formed by snowpack over long periods of time. How are these formed?
So rock glaciers form through snow accumulating in the very top of a cirque, so under sort of the shady side of a mountain. And it's not on a yearly basis, but you have a colder series of decades. So if we had a 2022, 2023 winter for 10 years, we'd contribute a lot of ice into a rock glacier. But they go sort of for periods where there's no ice exposed, they're not growing, they just are all rock, but then you turn on the snow for a few years and they get more ice contributed. And so you can see sometimes where the snow will pile on top of the rocks, and then that will be incorporated into the rock glacier. And so you'll see layering of rocks, ice, rocks, ice. And that records that sort of cyclicity.
Thanks a lot. That was great. Is there a particular reason why 3,000 meters is the number to see these at?
So it's a chicken or the egg question. I'd say there's just a lot of area in Little Cottonwood at that elevation. And it's actually a topic I'm researching with a colleague at the U, Leif Anderson, is rock glaciers grow where there's flat landscape that can collect talus and snow. And so that was the area that they could grow in, was that 3,000 meter elevation band. Not to say that they made that that sort of area in the first place, but that's where they sit. Thank you. Oh, Aaron, there's another one over here.
Thank you. So I was wondering, do rock glaciers deform and also creep the same way that ice glaciers do, or do they do it in a different method?
So it's a mix. Some rock glaciers definitely deform internally, and like the ice is deforming and they flow. Other times there's enough water under the base of the glacier that they slide along. And they're just such poorly exposed features, we can't really separate those mechanisms very well. Yeah, of course. You're welcome.
I have one.
Okay, Aaron.
So you touched on it a little bit, but how do you know that the water coming out of rock glaciers is from rock glaciers? And I think you touched on it with the stable isotopes.
That's a great question. So, so Aaron asked, how do we know if it's rock glacier water or not? Well, basically, yes, stable isotopes is the way to do it. And Jeff Moore, who's at Middlebury College, collected stable isotopes across the summer period and was able to show that there's a change in the character of the stable oxygen isotopes in the meltwater through the summer. So you're going through, he also collected snow samples and rain samples to correlate to, but was able to show that there's a transition from more snow melt dominated isotopes to this other signal, which he interpreted as ice melt. And you can also see it in like the temperature change through the summer too. Any other questions?
You talked about, or you've characterized the rock glaciers, and perhaps mostly for us to understand what conditions might persist even in a changing climate.
Yeah.
But is gathering this information important for some tapping into this as a resource that we can utilize somehow else, or that we're looking at gaining some of the water out of there somehow differently than we would naturally? Is that what we're suggesting with this?
Well, I think it's not so much that we want to go mine the rock glaciers for water, and forgive me if I'm misinterpreting your question, but it's more rock glaciers haven't been incorporated into our conceptual models and our numerical models of where is water coming from. We assume all the water is mostly coming from snow, and if we have a future perspective where we assume there's no snow in the future or much less, we're actually missing part of the picture. So we're trying to have a better understanding of the whole mountain hydrology in both the Wasatch but also the Uintas. And these are just features that haven't been accounted for, so to speak, so far. And that maybe in the future we won't have zero flow in Little Cottonwood. We might still have some amount of base flow contributed by these features that we weren't counting on or we didn't know about. So hopefully we can just provide a more optimistic view, but also an area we need to understand better, because we know so little about them. And then the biological component is another concern. If there are endangered species in the streams that flow out of these rock glaciers, that we want to understand those systems and understand what species are present. And that goes all the way to bull trout, which are quite a ways up the trophic levels from a stonefly. But they really like that cold water as well. I should also mention that if anybody has any interest in rock glaciers, come speak to me afterwards. Or if anybody has any money they want to throw at rock glaciers, also come speak to me. But yeah, are there any other questions? Sort of last call there. Oh, we got one in the back, Aaron.
So we go push a bunch of debris on top of all of our snow glaciers in order to have our more rock glaciers now?
So the question was, should we put a bunch of debris on top of our snow piles around in the winter to build more rock glaciers? And I presented to the Department of Water Resources and the Department of Natural Resources a couple months ago, and I was asked a very similar question: can we build more rock glaciers? And I mean, it's not a horrible idea. We could do that. It's like, whose real estate are you going to cover in more rock glaciers? That's the question. But yeah, thank you all for staying. I appreciate the questions in the audience.